That was a long, hard clip. We learned a lot. And there's more. One last edition of physics before we turn our attention back to astronomy, and we'll be equipped for most of the class, though we will have occasion to introduce more science. There is a lot to discover. So we're back to our understanding of light, which, as I said, is extremely important to us. And the first thing we want to consider are the possibilities for what happens when light meets matter. So we talked about dense objects like the Earth. When light hits the Earth, most of the light is absorbed. We know you shine a flashlight at the ground, it doesn't go through. Objects as dense as Earth take up only a very small fraction of space, but there are, in fact, large, cold clouds of dust and gas that absorb radiation, so they look very dark. So there is the possibility that dense enough and cold enough objects simply absorb light, or some of the light might be reflected when you shine a flashlight beam on the ground. Some of it bounces up. If you put your hand above the beam, you will see light coming off your hand. So we can get some reflection off of dense objects, and that in fact is how we see the world around us. Sunlight bounces off dense things, and we see them and don't walk into them. Now, in general, how much is absorbed can depend on the wavelength. So different materials reflect different amounts of the light in different wavelengths. This is how dyes and colors work. So the sweatshirt I am wearing is red because someone imbibed the fibers with a dye that absorbs, say, green light, and that makes the light that it emits look this nice dark red color. And other things, the walls behind me are painted with a paint that reflects mostly blue light, and therefore they look blue. And so what that means is that as we look around the universe and we see colors of things, sometimes if you see the colors of reflected light, you can conclude something about the chemical composition of the thing you're looking at. There is another interaction of light with matter that will be of great importance to us, and as we'll see, will explain interesting things, and that is the possibility that if you have matter that is not dense, that is tenuous enough to be transparent, so most of the light goes through, light scatters off of molecules, atoms, dust grains, anything, really. And the mathematical formulation was given by Lord Rayleigh in 1871, so it's called Rayleigh scattering. And what scattering means that a light beam coming in will hit some particle and be deflected at some angle. What that means is that you, looking here, will see light coming from over there that actually came from over there. You will see light coming from the wrong direction. Now, this phenomenon decreases with wavelength. Long wavelengths scatter far less than short wavelengths. So blue light scatters more than red. If you recall this image of the Pleiades cluster M45, we saw this blue wispy light all around. This is scattered light. These are clouds of dust around these stars, and the starlight is scattering off of them, so that light from this star that was not supposed to hit us on Earth, that was heading somewhere else, got scattered by dust over here, and so we are seeing starlight coming from the wrong direction because it was scattered by the dust. This has lots of interesting consequences, and one of my favorite is the following. In this experiment, we're going to simulate the interaction of sunlight with the atmosphere, and we'll learn some things. On the left-hand side, we see the apparatus. We have a cup of water standing on an overhead projector. The overhead projector has a round hole cut in a mask, and so what we see is we see the cup of water, and we see the light going through the cup of water and projected onto the wall. Water is transparent, and so looking through the cup and seeing the dark color, we're seeing the darkness of the curtains beyond it, just as were the air completely transparent, we would look above us and see the darkness of space. Indeed, if our Earth's atmosphere were completely clear, then, looking at the sun, we would see the bright white color of a black body object with a peak somewhere in the visible, The peak is broad enough that there's no distinguishable difference between the way our various receptors are excited. So any object with a black body spectrum of a few thousand degrees, like an incandescent light bulb, will appear bright white to us, as would the sun. The rest of the sky, though, when we're looking away from the sun, would appear dark. And this famous Apollo image that we see of Earthrise over the lunar surface is a great example of this. Clearly it is daytime on the moon. From the phase of the Earth, you can tell that the sun is directly overhead, as seen by the astronauts on the moon at this point. And you can see that the moon's surface is brightly lit, the sun is overhead, and yet the sky on the moon is completely dark. Had we looked at the sun, we would see a bright white sun. Looking away from the sun, the sky is dark, and in fact you can see stars in the daytime. This is not the situation on Earth, and the difference between the moon and the Earth is our atmosphere. To simulate 100 miles of air overhead with its abundance of scattering opportunities for incoming light, what I have done is I have stirred some reagents into this cup. Over time, as they react, they will precipitate increasingly large concentrations of small crumbs of sulfur into the water. These will serve as scattering centers and will allow us to emulate 100 miles of atmosphere in 6 inches. And what we're going to do is, as the concentration of sulfur increases, we will follow on the left-hand side what the cup looks like. This emulates what you'd see in the sky looking away from the sun, which right now is a dark sky and presumably star-studded. And on the right, we'll see what happens when you look directly at the light source. This will simulate what you would see looking directly at the sun. We've now achieved a sufficient concentration of sulfur precipitate that there's a lot of scattering going on in that cup, and the water is no longer transparent. In fact, we don't see the dark curtains through it. We see that it's glowing, and as predicted, blue light scatters more than any other color. So the color this cup is glowing is a bright sky blue, and as the precipitate continues to increase in concentration, that glow will get brighter and brighter. What we are seeing is sunlight scattered off the scattering centers in the sky, water molecules, dust particles, air molecules themselves, causing the sky to glow blue when you're looking away from the sun. And this is a very dramatic demonstration of what it is we're seeing. Looking on the right, we see what has happened to the transmitted sunlight. This is, remember, what you see when you look straight at the sun. Some of the blue light that would have reached your eyes had it not been scattered has been scattered in other directions in interactions with the atmosphere. This leaves the sunlight that reaches your eyes blue depleted, and blue depleted white light, you recall, looks to our eyes yellow. It's a combination of green and red with smaller amounts of blue. What we perceive that is as yellow light. This is the reason the sun looks yellow. We've now achieved a high enough concentration of scatterers that in fact when we look at the cup, it not only glows very brightly, but it in fact appears white. We see all colors of the light scattered towards our eyes. This is somewhat the color of a bright white cloud in the sky. A cloud contains many ice crystals. Light is reflected and scattered off of the ice. We see all colors reflected from a white cloud, so that's the reason we're seeing this. But we still have, as you can see at the edges where the camera is less saturated, there is still a preponderance of blue light in the scattered light, and this is very dramatically evident on the right when we see that the transmitted sunlight is now really a dark yellow. As the light loses blue components to scattering, what's left is yellow that is somewhat reminiscent of the color of the sun as we see it. We also see that as more and more of the light gets scattered, the observed sunlight is dimmer. Indeed, the atmosphere dims the sun by distributing some of its light in all kinds of other directions. The sun is much brighter on the moon where there's no atmosphere. Finally, having waited for the concentration of scatterers in the cup to increase to the point where, as you see on the left, the cup glows bright white, you can see that what's going on is that not only have the blue hues of the incoming white light been scattered away, but in fact it's lost much of its green, and the remaining color of the transmitted light, as we see on the right, is darker than yellow. In fact, it's an orange, and as scattering continues to increase, we will lose more and more of the green, and eventually the transmitted sunlight will appear almost red. This might remind you that there are circumstances under which, indeed, the sun in the sky appears red. I hope you found that demo as fascinating as I always do. What did we see? We saw that the atmosphere scatters blue light in preference over other colors, making the sky glow blue, and because of depletion of blue light, the sun appears yellow, so light of all colors impinges on the atmosphere, and the blue light scatters, so that if we look away from the sun over here, we see blue light scattered in our direction, among others, from the sunlight that hit over here, but the rays that penetrate are the greens and the reds. Together, blue depleted white light appears to us to be blue. And then, as we increase the concentration of scatterers, effectively making the atmosphere contain more impurities or be thicker, we saw when we got more scattering, we lost the green as well as the blue, and that left the sun looking distinctly red. And of course, the sun looks red to us at sunrise and sunset when it's low in the sky. The reason for this is both because at sunrise and sunset we're looking not through 100 kilometers of atmosphere, but through a few thousand kilometers of atmosphere. And moreover, most of the impurities in the atmosphere, the big scatterers, are at low altitudes, and the grazing rays of the rising or setting sun have more opportunity to encounter them and scatter. And so the blue scatters early, then the greens, then the yellows, and so on. And only at the end of the day, red light penetrates all the way through to our eyes. So that same demo shows us why the sky is blue, why the sun looks yellow, and why sunsets are red. Now, I can't resist a few other